You know, it's way more nerve-wracking being up here on a stage than it is being like lower level. So my name is Cassandra. I'm with Iron.io, and I'm one of your organizers for GoSF. Some of you might have seen me last night at the Rails Meetup as well. Saw a bunch of friendly faces. Wow. Major turnout. Are you guys like super stoked that the group has grown like 4 times in the last few years? It's pretty rad, right? Like, let's give ourselves a round of applause. Okay, I'm gonna do something really dorky. I like to start off the evening with a group selfie. So we're gonna do this right now, okay? All right, and this is going on Twitter. Cassandroid, that's my name, Cassandroid. I liked it, I thought it was cute. Okay. Wow, that's a lot of people. Wave, hey, look happy. One more, ooh, yay. Oh wait, did I get everybody? Okay, fun. All right, we're gonna have Mike come up here and give you a little info on Uber, our lovely host for the evening.
Hey guys, how's it going? Mike McClay, engineering manager here at Uber. Just wanted to give a little short history on kind of Go at Uber. It started about 2 years ago when our first production code went out. We were writing our external API, and we needed a system to kind of simulate all of the supply and demand dispatching requests for rides. So Aiden, one of our senior engineers, whipped it up pretty quickly over a weekend or so, and I'm pretty sure it's still being used. Juan? Yep, okay, awesome. So that was just kind of the beginning. Since then, or at that time we were a Python and Node shop. Since then, Go is probably one of the fastest growing languages at the company. We have about 300 Gophers on our mailing list right now. And across 3 teams on infrastructure, platform, and product engineering, we're all hiring Go engineers, and people are interested in coming and tackling a bunch of hard problems with us. So thanks again for coming out tonight, and looking forward to these talks.
Oh man, that's gonna get old fast. All right. Whew. I want to know who has traveled the farthest. And I actually know one of the guys. Man, I don't even want you to say it yet because I know. Okay, besides Finland, who has traveled the farthest to be here tonight? Anybody? Come on. I mean, Oakland. Yes. I'm an East Bay girl myself. Wait, where? Berkeley. I guess Berkeley is. Okay, well, I came from Hercules. Oh, we'd have to actually map that out to see if I came farther or you came farther. Okay, you win. Actually, Finland wins. All right, we're going to have Nick come up here and tell you a little bit about Iron.io.
Hello. Yeah, I'm Nick Sardo. I'm with the engineering team at Iron.io. If you don't know, we do platform as a service. We make it really easy to scale your code on our platform. You just upload our API, upload to our API, and we'll distribute it across Docker containers. We also have a message queue as a service, and we're hiring. We got a cool new office on 7th and Folsom, and we need people to help fill it, hiring Go engineers. So let's go around the room really quickly, find out who else is hiring. Raise your hands. Just say your name and like a quick 1 sentence of what you guys are doing. Go for it. Yes?
I work for Google. We are always hiring.
Google's always hiring. Who else? Yeah. Yeah. Great. Who else is hiring? All right, you?
I'm Dimitri from SourceGraph. We're doing code search, code intelligence, and we're hiring Gophers as well.
Great. Oh, yeah. Very cliche, distributed engineers. Yeah, just kidding. It's Go, that's what it's for.
On Twitch, we do live video on the internet of people playing video games.
Great. Okay.
Sarah, and we're doing container orchestration all in Go.
Yeah.
Square, right, upstairs.
Stop by on your way out. Yeah. Yeah. CDN. Yeah, that's fun.
Solar City, we're trying to save the world.
Woo! Great. Anyone else? Yeah.
Cloudflare, trying to save the internet.
Sorry, can you say that again?
Cloudflare.
Cloudflare, another CDN. Great. Yeah. And you get to live in Oregon. That's a great plus in my opinion. Anyone else? Oh, yeah, sorry. Yeah, that's a lot of fun. Great. All right, how many of you guys are using production right now? Raise your hands. Using Go in production, excuse me. Yeah, that's a good amount of you. How many for like the last 3 years? So you guys been doing it for a really long time. Yeah, some hardcore people there. How many of you, is this like your first GoSF meetup? Yeah, that's a good amount of hands. Great. And then I was having a discussion in the back about Docker orchestration tools, and this guy just brought it up. How many of you guys are using Mesos? Yeah, 3, 4 people. Swarm? 1, 2, 2.5. Well, I'm missing some other one. Kubernetes. Yeah, it's more the popular one, probably about 10 right there. Any others I'm forgetting? Nomad? 2, 1. Grinch? Rancher? Not familiar with that one. Great. Well, have fun. Enjoy the talks.
Thank you, Nick. All right, let's get. Oh, thank you. So, you guys might have seen I posted a community event on our Meetup page for the Gopher Gala. You might have also gotten my email if you signed up for it. They need to sign up for the event on their actual event page to actually participate in the Gopher Gala. There are a bunch of Gopher Galas happening over the weekend at Cloudflare and Segment. Did I get that right? Did I get that right? Yes? Good. So feel free to check it out. It's just gophergala.com and participate. There's some really awesome prizes on there, I must say. And they also have a jobs page. Okay, we're going to get really swaggy and learn all about Swagger with Ivan.
Hi, my name is Ivan, and I work for VMware. They sponsor me to work on Go Swagger, actually, not the entire time, but lots of time. I originally, I didn't always do Go. I did Scala before. I did lots of Scala for a very long time, and I wrote Scalatra at that point. I worked for Reverb, which is, if you follow the history of the whole Swagger thing, then Reverb is the company that came up with Swagger, and I contributed the Scala async Scala client to it. And then for Go, because as soon as I went with Go to do distributed systems, I forgot all about Scala, and I needed Swagger there. So I started writing the design first approach for dealing with Swagger with APIs through Swagger. So I think this is a conversation most people have had at their companies at this stage, which is, we want to do microservices. Microservices are great. Everybody agrees that microservices are a relatively good way to deal with this segregation of teams and all of that stuff. However, there is a problem that you get with microservices. Like, you have to document these things. There's going to be lots of these, though. So you have to document these things. Documentation is kind of nasty, but it should be about 50% of your project, because that's how all the other people deal with your project. Documentation gets stale over time, so people don't actually update it. And then you kind of end up in this place where you have to communicate quite a lot between all these different teams. Swagger sits in that sweet spot where you have an Android app and you have an iOS app, you have a web front end, you have a bunch of backend APIs. Everybody needs to kind of talk to each other, but we don't always talk that well to each other or at the right times when somebody makes a breaking change or adds an endpoint. So you get into this point where the backend team is the original bottleneck, because the front-end team will have to wait for all the APIs or at least some stubs to be delivered. This also puts a lot of burden on your customers. So these people now have to write your SDKs. because they read those markdown documents and those fancy websites that people build about their APIs. And so all too often that leads to relatively lots of sadness. There's conflicts between teams. They're like, oh, that guy didn't deliver my stuff, and all of that is just not super fun. It leads to cover your ass and just not a good place to be. So with Swagger, we went with people want up-to-date documentation to read, preferably with just also like actual text. Then consumers, by consumers here, I mean actual software systems. They like strong contracts that describe what is going to happen, what the inputs are, what the outputs are going to be, maybe what specifies valid input and valid output, stuff like that. If you, I've mentioned earlier the iOS use case and the Android use case. Those are vastly different platforms, different languages. So you need SDKs in 3 languages at the very least if you're doing some mobile kind of thing. Then if you're running this microservices architecture where you have thousands of services running around in your system, it would be nice to be able to reflect over them, maybe like reuse some of the models that these people define and recompose them together in a place like a load balancer. And this gives you another level of dry. So Swagger kind of takes care of that contract in those documentation bits and pieces. So you end up in a place where you're deploying lots of times because continuous delivery seems to be a thing. You end up with this vast array of services that you need to reflect over. And at this stage, tooling for APIs is relatively primitive. We can all build APIs and go as a super interface to do that. But running those APIs and getting insight into those things and all of that stuff, everybody is still growing their own. We haven't really actually solved those problems yet. So what Swagger is an open standard that is being contributed to by lots of bigger players, also some smaller players. It's up on the Linux Foundation. It's always been a kind of a community-driven process. It's an interface to your service described in JSON, which makes it language agnostic, because pretty much every language has a JSON parser. They're also relatively trivial to write. And it gives you this language platform agnostic contract for your service. So people who want to talk to your service actually know what to do and what kind of input to send back and forth. It enables it's not a REST in the terms of, oh, you have to do REST, and when you delete, you have to use the delete verb and stuff like that. Not every company works that way. Not every team works that way. Sometimes you have to do a get with some flag. So that's what the bigotry-free RESTful design is for. It just wants you to get on with your job. It's machine readable, so that means that you can kind of build tools that start juggling with those specifications in particular. And it's server controlled. So the API that you're documenting is actually serving the documentation for itself, meaning you can also host like, we'll see some of this in a little bit later. You can host a UI that people could interact with your API and all of that stuff. And it's all driven through that meta description. So Swagger comes with a bunch of tools. I'm going to talk more about the ones that I built and I'm building for the Go community. But some of them, or lots of them, exist in other languages as well. Obviously, the JavaScript people are at a slight advantage because it's all JSON and it kind of works well for them. So the first thing that we've got is you get a bunch of validation. So when you start writing these contracts, in a design-first approach, I think maybe this scenario might resonate with people. You start a new application, so you go into something called a design meeting. In that design meeting, you've got a bunch of stakeholders, and everybody is discussing, oh, we should have users. Yes, users is a good idea. So you start designing that user, that user representation, and you do that immediately in that YAML document. You add some documentation, because the documentation guy is right there, and he's like, yeah, we should do this and that. Then you want to create those users, you want to delete those users, so you're going to define these endpoints, and you can do all of that in that same meeting. When you walk out of that meeting, you want to first check if the spec is valid. That's the first thing you want to do. Once you get that, you can actually start generating clients, and you can generate a server for that. You can stop that server with mock data. So at that moment, you're serving meaningful data for your client people, right? They're going to be very happy with you. Spec generation for any application. So let's say there is this guy on the internet, APIs guru, and what he's been doing is he's been spending his nights like writing Swagger specifications for GitHub and for a whole bunch of APIs out there. So there's like he's got like 300 APIs described as Swagger specification. Point this tool at it, and you've got a client for it. You've got a Go statically typed client for that API. In a matter of seconds. Documentation lives with the code, so in the version that I've done, that part is actually agnostic of any framework. And so whenever you update your code, you should also update the documentation that comes with that block of code that you just updated, and that will end up in those specifications. So people will be it automatically keeps itself up to date, and you can use Go generate in your comments, and then use that pre-built step. So the clients that it generates are not interface. We shun interface in these things because we already know everything. So if we can avoid falling back to interface, it's going to be a fully statically typed client. It is regenerated whenever you tell it to regenerate, or you can look at a spec and see if there is a difference. This is originally we did this to enable mobile teams and to enable web front-end teams. But actually, when you go to a microservices architecture, everybody's very happy that that one guy that everybody depends on, he made one change, and now everybody has to regenerate. But it's only a matter of a few seconds, and they're back to where they were. They get some compilation errors, but that's good because you want to know when things break. There is, in Swagger CodeGen, this is a hosted service that you can use. There's about 30 different languages that you can generate SDKs for. Now, some of these SDKs aren't as great as other SDKs, but the Python one, the Scala one, Java one, and Node ones, they should all be top-notch. And Objective-C, and then whatever the Tizen stuff, they were sponsored contributions, so they're definitely relatively good. Then for the Go Swagger, there is a server. I took the stance that the spec needs to remain the source of truth, although you need to be able to edit your code and regenerate a spec from it. The spec could be used as a point during your meetings. It gives you some Swagger metadata, so it's going to serve up that spec as promised, but on top of that, it's going to provide routing. It uses a router called Dinko for this. It applies security, the security things that Swagger supports, so that's basic auth, OAuth2, stuff like that. It does request input validation, and if you really want to, output validation. And it's built on top of Go middleware, so any of the other middlewares that you got, you can just plug them in and use. But it's going to take care of that API bit. So what that means is you generate the code, and then you just fill in the blanks. You just fill in the business logic, anything that's not repetitive code. Because in the end, writing a web API is kind of boring. The first part is relatively boring. You always have to do the same thing. Is the string not empty? Oh, OK, cool. I can move on. So it's going to take away all of that boringness. That was the idea. So knowing not everybody wants to be on the bleeding edge, especially not when I'm writing that API, that server bit. So there are other frameworks out there like Gin and Bigo and all of that stuff. So how would we enable these people to generate Swagger 2.0 specifications? I came up with a set of, I went out and I took documentation comments, and I provided a bunch of annotations that you put in those documentation comments. The one thing, there is one leap that I did ask for people to make, and that is whenever you use a type, it wants you to document a struct, because why else use a compiler if you're going to duplicate all the type information? So that was that's when you describe parameters and responses and stuff like that. You're able to compose them out of different structs. But everything else works with these documentation comments. It parses. This is a route definition, so it's going to serve up something that updates to-do lists, to-do items, and then these are the parameters for it. And this works at also with GoGenerate, so it's prior, no reflection involved. Later on, when you finally got that little API thing going on, you're probably going to want to interact with the API. You can use curl. It's going to get a little bit tedious. Lots of people tend to use something like Postman or something. So you can take Postman and you can point it at a Swagger specification, and immediately you get all of that filled out. You get a UI actually to interact with your API. There's another tool like it that's called SOAP UI. That comes with test integration, so it's going to kind of like build some integration test suite for you. And then if you really want to provide a CLI, you can use at this moment it's a node tool because I didn't get to that ticket yet. You can use a node tool to generate a CLI for your API. So I've put this slide in here just because I'm sharing it online. And then you guys have a bunch of links that you can go to. There are some things that I wanted to show. So we've got a Swagger editor. And in here, you get this. This is my Swagger document that I wrote one evening. It's what I used to like sanity check. Basically, it's got everything you get in an API. You define what comes in, right? So I want JSON. I'm also going to output some JSON. I want this to go over HTTP. I want to do find. I want to add to-dos. And I want to update them. And I want to destroy them. Other than that, you define a model where you can say, oh, these fields are required. I want something to be an ID with a long. And I want a string that is at least one length, one char long. So while you edit this, so if I were to make a mistake and say something like this, it's not going to be happy. So that it does this in real time. Now at this stage, one of my gripes with this one is that I can't share at this moment. So now I'm just editing. There is this project called Swagger Hub, where you get a similar type of environment. It's the same spec, does the same things. If I make a mistake, it's also going to be not happy. It gives you the more, you're probably going to be, if you've ever looked at Swagger, this is probably the one you've seen before, where you get this UI kind of to deal with this. Most people tend to customize this very heavily, and sometimes there's cursing. But this one is the one I use most of the time. Then one thing I wanted to note as well is often people will walk up to me and then they go, well, we're using RAML. What do you think of RAML? Well, RAML is cool, but this is what I think of RAML. So, are there any questions? Yes. Swagger? Originally, there was this project called Waddle, which is kind of like WSDL, but for web applications. This XML is horrible, so we said, why Waddle if you can Swagger? I worked for WordNick, so words were kind of a thing. We did this machine learning thing on top of the English language. And so, yeah, words were a thing. Very good question. I should have mentioned this, actually. So Open APIs is the new Swagger. But it's where all company sponsorship has been taken off, and now it's in the Linux Foundation, and we get people like Google and Microsoft, and everybody is now in on the conversation, and we're all going to fix JSON schema. Yeah, that's the idea. Personally, I think OpenAPIs is very good because it's actually the one thing where there is no vendor trying to shove down its toolset down your throat. And everybody can participate in that conversation. You don't have to pay a huge membership to be part of the mailing list, right? You pay for that logo on that page at the bottom. Yeah. Yeah, I have to rename it at some point. Although I'm very happy that people are finally starting to use it, and I'm finally getting to a point where it's kind of usable. Lots of thanks to the people to Chance, for example, who's been testing and submitting bugs and all of that stuff. So that's been very helpful for me. And so I'm kind of reluctant to start to rename it at this very moment. Maybe I'll rename it a couple months down the line. Everybody kind of knows what Swagger is. And I hope everybody kind of knows it's been renamed. But until there is like, I would say until the next version of the spec comes out, I may not want to rename it. Because it would just be a rename for the sake of renaming. Yeah?
You said that people can generate code from specs or specs from the code. In your experience, what do you think people do?
That depends where you are in your development process. So if you're early on in your development process, I would say you kind of want to come out of those meetings and regenerate code, right? Now, when you come back, and the way I've designed my code generation at least is it will never overwrite your own code. So the things you're going to plug in, they're always going to be safe. If you write them in the right files, or not in the files that I'm generating, right? So I think that often you get like these, oh, there's this one quick feature we have to do to make this one demo, right? Then you edit your code, but your Swagger spec needs to get updated. At that point, you're kind of happy that it's there. Also, I recognize that not everybody like uses a tool that might blow up in their face at this very moment. If you already have an API, or you're more than happy to do all your validation yourself and all of that stuff, which is your good right, then that's where this sits. So I wanted to bring the goodness of Swagger to the people.
So are you saying that if I generate Go code from the Swagger API,
Yeah.
and I can generate Go API from the Go code,
Yeah.
I get the same API?
You get an equivalent API. Yeah.
So yeah, I have a question too here. So yeah, very nice talk. Thanks for coming. Actually, really helpful. So one question I had is like, how do you have any backward compatibility support? So like, how do you make sure that your new changes doesn't break the old API?
The APIs, you mean? The APIs? Yeah. Or I thought you talked about my tool. So for APIs, actually, that is a relatively simple problem to solve, because now you've got your API defined, like it's a JSON document. If you order these keys, and then you can use diffing. So JSON diffing. If you get adds are fine. If you get updates or deletes, you should stop. You've just broken things. So. In the interest of process, just don't update or delete. Right? Yeah, so for me, at the top of my list, once I get through rendering all the JSON polymorphism things, the question is there interest, or how do you think about Thrift and protobuf and all of these things? I think protobuf is an awesome wire format, just like Thrift is, but they're not a full solution to what the contract first kind of approach. But luckily, you can kind of build all of these things dynamically, and you can generate code that generates protobuf, right? So if somebody were to come along and plugged in code in a template that renders these models as protobufs, I wouldn't be opposed to that at all. I would love it, actually. And so that's one of the things I've been looking at. I know there's a Proto-Siege and Swagger for the gRPC project, for example. I know there's a kind of a mismatch between the two. And I want to investigate, but I still need to get to the first feature complete before I start doing whistles and bells. And I need lots of help. So if you're interested in contributing to a relatively large Go project that I think is kind of useful to people, feel free, right? I'm not going to stop you. So what's next? That's the last thing. What's next? I wanna make use of the HTTP 2 story a lot more than it is today. For that, I had to submit a bunch of extensions to the Swagger specification as well. I want to integrate with Swagger Cogent. That's one of the things that's going to happen in the next month. So then I want to implement the actual stub generation bit so that you get those stubs immediately. This generation, I wanna end up at a place once you've generated code for your client and your server, you get 100% code coverage. I like to say it can only go downhill from there. So that's where I want to end up at. And then I want like an HTTP IE. I don't know if you guys know HTTP IE. It's a very nice command line curl on steroids kind of thing, Python thing. I want to use that syntax to create CLIs and generate Z completion for that. More transports. By transports, I mean it's HTTP is my abstraction, but I can do HTTP over RabbitMQ. I can do that over ZeroMQ. I can do that over anything really. I've done a proof of concept for RabbitMQ that was about 100 lines of code, and all of a sudden I had contract boundaries over RabbitMQ. Scriptable handlers, that might not be the right audience here, but you could implement a handler in Python. Right? And protobufs, message pack, these kinds of things, the ones that are amenable. Like I think Thrift and Avro might not be super amenable to this kind of dictionary look at things. Okay. That's all. OAuth? Yeah. Yeah, should be easy enough. Yeah. Is it easy to integrate OAuth? So you mean OAuth 2, right? Yeah. So Swagger actually has the support for OAuth 2, and you use any library, and you make your login form and stuff like that, and specify the URLs, and you're good to go. Yeah. Are there more?
Why does VMware care about this?
Good question. So VMware is getting into interesting cloud native apps, containers, and all of that stuff. And I actually also built other things that I couldn't open source prior in another company. So I like everything that's cloud, right? So to me, I think parts of cloud native apps and the things that people who are in the cloud native app space are always neglecting are the apps, right? And that's actually why we're doing this. And Swagger is about the apps. So I think that's why they kind of like let me do my thing there. I run around there. I work half the time. I work on Swagger kind of. And the other half of the time, I have to look at Kubernetes, which is good, which is an awesome tool, and drive Kubernetes within VMware and our contributions. Okay. That's all.
Right? All right. We're going to have Matt come up and teach us all about Snap.
Hi, everybody. Hey, I'm Matt Brender. I'm a developer advocate in the software-defined infrastructure team at Intel. And you're probably curious, why does Intel care about software? Okay, so I'm going to tell you about what we're doing in the software-defined infrastructure team. We're focused on orchestration, automation, and schedulers, particularly as you think about how Intel can be consumed at a greater amount, because the more hardware you consume of ours, the more our stock is worth. And from this fun angle is why I decided to come and focus on our open source software contribution. So our first project is called Snap. This is a Snappy, the turtle. This was actually drawn by one of the core developers. We're going to make some more pretty things, Docker-esque and Go-esque in the long run, but that's not what I'm here to talk about. I want you to go write a plugin, because what I'm going to teach you about is a telemetry platform that is truly open, easy to extend, and I want you to do so. So first, what is it? Snap is an open framework for metrics. We're talking about telemetry, but everyone has this idea of telemetry. You either think like satellites trying to bomb things or rockets going into the air, but we're talking about CPU counters, we're talking about smart data off your disk, but it actually goes further up the stack as well. What we're not talking about is a sort of analytics replacement. Snap is very intentionally designed to be a flexible framework which you can collect from any quantity of telemetry platforms and instances and push that through a system in a very agnostic way. We're not trying to compete with this tool set with New Relic or Datadog or anyone like that. We actually think this is a great way to pull information out, normalize it into a single catalog of information, and push that up into an APM. So there's 3 processes. There's 3 different plugin types, and you'll see that all throughout. There are the collectors, the information that you gather from. So it's a little Go process that will actually pull information. So there's some that pull from files, info pulling from proc. We've got a collector for Docker, and so it can be hardware specific, like we've got Node, DCM, NIC, disk, a ton of information that you can pull from Intel specific hardware. But this isn't just for Intel specific hardware. We actually designed it intentionally so that others can extend it and get a single catalog of information from their whole platform. But we're also pulling from other telemetry and very common age-old instances. CollectD is in development right now, but PSUtil is something I'll show you in a little bit. Factor for the Puppet people out there, and so on. From there, we intentionally made a middle part, a processing state, where you can do some sort of normalization or make some secondary metric off that original information that you collected. This is where some of the smarts of the system can really shine. Right now, we just are doing a floating average. So there's a lot of room for machine learning algorithms, for encryption analysis, for really fascinating things in the middle. And then it's incredibly important to store it somewhere. We're not storing this with any sort of longevity. We're very much designing a process that just pushes it off into the next platform. So whether you're pushing it to a messaging queue or some sort of database, you can choose and write the little plugin that will do that for you. So what that produces as you collect information is a single normalized catalog that's queryable in a standardized way. So as you collect that information, we'll add to a catalog, and as you load and unload plugins, it will get to a state where you have a unified view of it. So if you have plugins that collect the same metrics, you will actually just have one of those. So you'll have a nice, clean view of whatever world you're consuming from. And we'll talk more about that. And then you push that in a single, clean way down through your publisher. And really, the call to action here is that we have a growing list of plugins. We're publishing some of the projects we're working on have to do with pulling from Docker, from VMware, and then pushing that down to RabbitMQ to Postgres. So let's just play with a demo. I want to just show you what snapd looks like, the daemon, and then load one of the first metrics. Okay. All right, so we're going to spin up the daemon. Every plugin is designed to be able to be signed. So I'm actually going to say no signing right now because I just want to throw in some mock information. But this is great for people that want to have some sort of certificate authority in their system, some sort of control over what's being thrown into your telemetry system. It's also great for partners so that they can make their proprietary bits on top of this open source software so that we can get a nice rich ecosystem. And I'll just set up some logging here. Good, so snap's running. And need to plus that guy up. Yeah. Okay, so if we do if we look at snapctl, we are able to see the collection of what metrics we have. And just to note, we're currently in beta. The main thing that we're waiting on to go into GA is actually going to be sticky routing so that we can break out the collectors, the processors, and the publishers into separate nodes and actually have that in a more distributed fashion. Right now, they're co-located in a single binary. And that's something that obviously for scale is going to just be amazing. And we're working on right now. You can see that all on GitHub. But snapctl, if I do a metrics list, while we don't have anything here, we've got very much nothing interesting. But let's load one. I'll just steal this because it's easier. We're going to load a plugin. I've built this plugin in another directory, so it's something I went and go get. It's actually the PSUtil collector. So we now have a catalog of metrics available to us. If we start running this, you run things using a task. It's either JSON or YAML file that you define, and it says the frequency and from where and where you're passing it to. But if we check out what we're able to gather now, you'll see the nice, pretty catalog that I was talking about. And it is insanely long. The trouble with telemetry in the past is that there's either a lot of it or not enough, and it's impossible to normalize. So what we're trying to tackle with Snap is really normalizing it through a nice, clean namespace. So you see everything that we're producing as a plugin is going to start with the Intel namespace, and PSUtil is where you're collecting it from. If we're gathering information out of proc, it will be /proc. If we're gathering it from Docker, /Docker, and so on. So real simple to do. So we have that, and let's add one other. Bin snapctl load plugin. I think it's here. Plugin, and just one other to check it out is the snap collector, just a mock one. We're just gonna not worry about that. I'm gonna just unload the other plugin that we mentioned. So just to show that we'll update that catalog. Plugins, the question was, how are the plugins written? Right now, they're all written in Go. There's very simple, just two interfaces you need to line up with in order to be compliant and able to run. And we have some insanely good documentation on that that walks you step by step through making a plugin and also the best practices around it to make sure it's efficient and well written. That said, everything's written in Go right now. There's nothing stopping people from writing it in other languages and just keeping true to the RESTful API that we set up here. But you'd be the first, which would be great if you want to do that. But given the audience, yeah, pretty easy to do in Go. Plugin, unload, and we'll just unload this collector, which is PSUtil, and it's version 5. So now if we did a bin snapctl metric list, we now are gathering no information. Ta-da. So I wanted to show you the dynamic nature of the catalog. Thank you. Okay, so all we did, we loaded some metrics, we unloaded them. I really wanted to show you the dynamic nature of this, that if you imagine this at scale, you can have a fleet of Snap nodes in, whether they're in your container environment, in a virtual growing environment on AWS. What's interesting though is that, when people talk about telemetry, again, they think about the hardware, like we want to expose the Intel interesting hardware, but it's definitely not just about the hardware. The way we're looking at it is telemetry goes up through the orchestration tier and up into and leading up to the application. So we really don't care where we're gathering the information from, whether it's PSUtil. We'd love to write something to collect from Prometheus so that we're able to play in that ecosystem. We're working on collectd right now, and we have a bunch of specific things for Intel hardware so that you can see it in a single catalog. Whether it's going to roll up into something related to your actual servers. And then you're going to define tasks, and those tasks are going to happen at some sort of, whether it's milliseconds or seconds, the timeline is up to you based on whatever metric you need to. You're going to pass it to something, like some sort of filtering, some sort of analysis, and then you're going to push it to something. And you're going to publish to, say, Cassandra if you're using that, and then you're going to visualize it somewhere else. So Grafana is a common way to visualize that for your ops team. But you can see it breaks down into those 3 categories of collectors, processors, and publishers. And just, asking for help here. We need all of these. We need collectors for Prometheus. We need people that are interested in Bayesian filters and the smoothing of analysis of a lot of noisy information. And we'd love to publish things to Cassandra. So go write that. The things that make this really interesting, especially when we compare it to what's out there right now, from StatsD to CollectD to everything else that ends in D, the lifecycle management is really crucial here. That we found that all the telemetry frameworks, they don't have this hot swappable, very modern nature to them. So when we load a plugin, there's no restart. The metrics are updated right in line. When you're actually swapping them, it's a single transaction. So it's very smooth, and it works the way you'd expect it would. The deployment's really nice where your collector doesn't have to publish to just one place, and it doesn't have to have a process in between. So you can go collect to multiple publishers, collect to multiple processes, to multiple publishers, ad infinitum. You can scale that pretty nicely. And the last part is called tribe, which is actually the effort we put into automation. So we're using a gossip-based node-to-node communication so that you set up a seed on a single one of the Snap nodes, and you're able to give a plugin or a task to that node, and it will propagate it to the other nodes in that tribe. And actually, if I could get assistance one more time, do I have a volunteer? Yes, I do. Yeah, come on up. Hold my microphone. I want to spin up a few different nodes of Snap. Initiate a tribe so you can see what that looks like, and then load multiple plugins so that you can see how that looks. Thank you. All right, so we got one Snap running. I want to run a couple more. So in each of these, we're going to do bin, snap, d. Need to cheat a little bit to make it easy because the syntax is pretty damn long. So we're going to initiate a tribe on this snap daemon. The tribe port, so the port in which you communicate that you want to initiate it, is going to be over 6,000. Give it an IP address, and we're going to call this seed. So that's running now. And now let's communicate with that guy from a second node. So I'm going to spin up another snap daemon. Okay, spin up another one. We're going to give it a separate port so we don't have a conflict there. And then we're telling it to talk to the port on the seed that we just set up, and just calling it a node member, which I also have a variable in because this is in a script. And let's just call this guy member 1. You can see that he recognized that he just had a member come online, and we added that. Let's keep doing that game. Okay. So great. We've got 4 different Snap clients running, or Snap daemons running, excuse me. And now we're going to use snapctl and actually, well, let me show you what that looks like. Well, yeah, let's load a plugin now. The same one we were using before. That just worked. Okay, so when you set up nodes into a tribe, you set up a seed, and then all preceding members that you point to that seed on that specific port is then able to communicate and actually establish a set of tasks and a set of plugins in which it will slowly propagate and catch up. So eventual consistency, which is really nice at scale. We've tested this in the hundreds. We're aiming to get up to 10,000 and make sure that this propagates cleanly, so that you can think of having a fleet of servers that, instead of having your own sort of automation that you need to worry about for Puppet or Ansible or whatever config management you're using, you actually just use this by talking to one node in Snap, and all the other nodes in Snap communicate or keep up with that. And you can have overlapping tribes. You can have some section that are picking up PSUtil information, while another section are picking up smarts data, and it can be a Venn diagram with some in the middle using both of them. So you're probably curious why we're using Go here. Go hasn't been used a lot at Intel that we know of just yet. We're the first ones going public with an open source project, and we're advocating a lot for it growing in the team. It just felt right when you think about these three things. The tool set was wonderful. We're using Logos. We open source something called GoMit, which is actually an event scheduler that we'd love for you to use if you need something that's a nice, clean event library. And things like member lists to be able to pass around some key values. And we actually, talking to all the core team members, they really liked that somebody was the arbiter of everyone's strong opinions. You got a lot of strong opinions from a lot of smart people on the team, and nothing like Go format to just like not have an argument over how many indentations you should have in your files. I also really appreciate the testing. I consider it a first-class citizen, and that is not often enough the case when you look at infrastructure in particular, which leads me to the last part, that the amount of momentum in infrastructure development is insane right now. CoreOS, Kubernetes, Mesos, Docker, obviously, and all the projects from HashiCorp are just killing it writing Go. So, it's hard to fight the rising tide, and we don't want to. It's a great language, and we are happy to be on board with it. So I just wanted to actually say thank you, because if you're any part of this initial launch that we had, we were trending in GitHub for the first 10 days of our launch in December. We've got over 500 stars right now, and had some love over Twitter and some really funny GIFs, given that Snap is the name. There's a lot of room for OSnap jokes. So I highly recommend you take a look, especially if you have interesting information that you want to propagate up, push it downstream, and add some value to your infrastructure or to your application by being able to normalize that information. We spent, even though we're in beta, we have 10,000 lines of documentation, and that's just on top of what we've already written inside the actual core code. And then we've been up on Gitter having a great conversation with people, and we're pretty easy to find. So would love for you to contribute and reach out to us. Other questions?
What happens when the seed dies? Is there any way to continue to add new Snapd members to the tribe, or is it kind of just like a single point of failure there?
Yeah, I think when the seed dies right now, I think it's you're left with just your existing tribe. Some sort of election process is a great idea. I just don't think we were going to put that investment up front. The lead developer on that part of the project is actually playing around with etcd right now, and I'm not sure what's going to come of that. But yeah, we're not doing an election or anything fancy like that just yet. All right, thanks everyone.
All right, Prashant is going to talk about Go profiling and optimization. He's going to get ramped up though.
All right. Hello, can you hear me? Awesome. All right, so I'm Prashant Varanasi, and I work on the RPC team here at Uber. My role in the team is to build Go bindings for services, and a lot of the work we're doing is actually open source and available on GitHub. Look for T-channel on Uber's GitHub page. I also spend a lot of time on the Go ecosystem here, which is relatively new compared to the Python and Node worlds at Uber. Before Uber, I was working at Google, and that's actually where I started using Go, and where I learned a lot about the language and idioms and so on. In today's talk, I'm going to focus on profiling and optimizing Go. I'll cover the tools and technology at a pretty high level, and then we're going to jump into some code, and hopefully the demo gods will be a little bit nicer to me. So, pprof. Go has pretty powerful profiling built right into the runtime. It's accessible through the pprof and runtime packages. Pprof is a sampling stack profiler. What that basically means is that periodically, it will check what's running on the CPU and record that. It also does heap profiling in a pretty similar way, except instead of checking periodically, it looks at some small percentage of allocations. The runtime creates profiles, which are then analyzed by the Go tool pprof. You can generate profiles using the standard tooling when you're running tests or benchmarks by passing -CPU profile or -mem profile, and we'll play with that in a little while. You can also generate profiles on running services by, if you blank import, that's the underscore import, the net HTTP pprof package. This adds /debug/pprof endpoints to your HTTP server. When you hit this endpoint, pprof will start profiling for a short period. You can choose how long. By default, it's 30 seconds. It'll then record a trace and send it over HTTP. And you can hit this endpoint directly from pprof, as you can see in the slide. At Uber, we recommend enabling these endpoints by default in most of our backend services because there's no overhead when you're not profiling. And it makes debugging a hell of a lot easier when you do see some unexpected performance or problems. For example, in one service, we saw a spike in the number of go-routines. That's what we got from our metrics. And then we used pprof to go to the /debug/pprof endpoint. We were able to look at exactly what stacks were running, and we could use this to pinpoint exactly what was stuck. And in this case, it turned out that we had like 10,000 go routines stuck on writing to some channel because no one was reading from the channel on the other side, and we were able to fix this really quickly. Without pprof, this would have been much, much more difficult, and we would have just had to restart our servers and hope that it doesn't happen till we figure out what exactly is going on. So to analyze profiles, pprof has a command line interface. It kind of lets you dig deep into exactly where time is being spent. So you can dig into a function and look at a line-by-line trace of exactly where time's being spent. Or you can even dig really deep and look at exactly which instruction is using up your time. It also supports a more graphical view. You can use the web command or the SVG command to generate graphs like this, which make it much easier to see the flow of the program. They give you a better high-level understanding of where time's being spent. But as your programs get bigger, these graphs also get bigger, and it can get a little bit difficult to figure out exactly what's going on. And that's where GoTorch can help. GoTorch is a tool we built here at Uber to generate flame graphs from Go's pprof output. It takes advantage of all of the built-in pprof capabilities, but renders the data in a different way. We wrote this tool because flame graphs are more familiar to Uber developers. We've been using them with Node and Python already. So in a flame graph, the y-axis, so you can see this y-axis here, it's showing the stack depth. The top function is what's running on the CPU. This top box here represents what's actually running. Everything beneath is the list of callers. Unlike most graphs, the x-axis doesn't represent the passage through time, but it's alphabetical. This is a big point of confusion for users dealing with flame graphs for the first time. So remember, the x position doesn't matter at all. However, the width does matter. That essentially tells you that a function is spending more time on the CPU. This can happen because it's been called a lot, or because one function just happens to run for a really long time. Contrary to what you might expect, these colors don't have any meaning. They're randomly chosen to be yellow and red, hence the name flame graphs. You can learn more about flame graphs on Brendan Gregg's homepage if you're interested. So GoTorch generates these flame graphs from the same pprof profiles that are generated through tests and through the NetHTTP pprof endpoints. So now that we have a high-level understanding of the tools, let's jump into some code. So we're gonna, let me make sure you can hear me. So we're gonna play with a simple web service here. Let's jump into the main function. So our main function here has two handlers being registered. They're both actually the same handler, just that one is registering the handler directly, while the other is wrapping it with some sort of metrics emitting middleware. And then we just have an index page. The index page just links to these handlers. Let's have a look at our handler. It's pretty much the simplest handler you'll see. Write hello world. That's all it does. And then we have this with stats thing. So let's have a quick look at that. The with stats middleware is basically wrapping the handler with some sort of counters as well as tracking latency. So this kind of middleware is pretty useful when you're writing a HTTP server so that you don't have to replicate recording metrics at every single core site. You'd use middleware for this. Now, let's run this server and have a look at the actual program. Oh, there we go. So our server started up. refresh our page, it's got links. We hit the /hello endpoint, it says hello world. Hit our /simple endpoint, both say hello world, just like we expect. But there is a difference in the stats. So if we refresh the simple endpoint, nothing's happening. If we refresh the hello endpoint, we see that it's recording stats, right? We're seeing a whole bunch of metrics being emitted, which include things like the host name, the endpoint, the OS, and the browser. Now, let's say that someone came to us and said, hey, this hello world endpoint is just too slow. We need it to be way faster. So what's the first thing you do? So this is where you would come into profiling and optimizing. First thing we're going to do is benchmark our handler. So I'm going to use a load tester that's actually written in Go as well. Tell it to use 80 Go routines and for 5 seconds hit some specific endpoint. So in my case, I'm going to hit simple. And runs it and tells us exactly how many requests it made and tells us requests per second. So in this case, our simple endpoint, it's pretty good. It's got 58,000 requests per second. Now let's try our hello endpoint, which is emitting stats. It's actually going to be a lot slower because I forgot to disable prints. We don't want to slow it down just because of the prints. Let me just turn that off. Let's try again. All right, so we're going to run our hello endpoint. And it's going to be slower, but let's see how much slower it is. There we go. That's a pretty big difference, right? What were we seeing earlier? I think it was like 58,000, and now we're seeing 38,000. That's pretty bad just for emitting some stats. So let's figure out what exactly is slowing it down and optimize it. So to do that, I'm going to use the net-HTTP preprof endpoint that I've enabled here. So if you look at my main.go, I have this blank import for net-HTTP preprof. So we'll have the HTTP preprof endpoint running. And because we want to be able to profile when there's some load. Otherwise, there's going to be nothing useful in the profile. So let's have some background requests being made to our hello endpoint. It's going to run for 500 seconds. That should be plenty. And we can look at the pprof endpoint. Let's do that. So this is the basic pprof endpoint. Doesn't really look that fancy, but you can see a lot of information here. So for example, Go routine tells us, hey, there's 92 Go routines running right now. But one of the more useful things is that this prefix here tells you how many Go routines are in this specific stack. So in this case, we can see that there's 82 Go routines essentially reading from the network port. So the runtime is doing some network reads for us. That tells us that, hey, there's probably 80 requests that are pending right now. There's also some useful information in heap. The top of this isn't really too useful for us mere humans. We need to use pprof. But the bottom of it is where the useful stuff is. So runtime.memstats gives us useful information like how many allocations have I done? And maybe more importantly, how many garbage collections have occurred so far? And how long have the garbage collections been going for? So this is actually showing us the last 256 garbage collections that have happened. And we can see that if we refresh the page, number of GCs is going up, so 2146, 2180, because we have a lot of requests going on in the background. So this still doesn't really help us debug why our program is slow. This is where we need to use the pprof command line. So we go pprof. We have to tell it how long we want it to profile for, otherwise it does 30 seconds, which is a little bit too long for us. So let's say 5 seconds. I think it's, there we go, 5 seconds. And then you need to specify which endpoint you want to hit because pprof is capable of different types of profiles. It can do block profiling for contention. It can do heap profiling for allocations. In this case, we care about CPU. So that's /profile. Let's do that. Let's get the profile. And once it's done, it saves the profile, and then we can kind of look around at what exactly is using our time. So there's a bunch of commands. The most common one you'll use in the command line is top some number. Here it's showing us the top 10 functions which are using time. Not particularly useful, so let's try top 10-cumulative, which shows you the function and any functions it called. So that's a little bit more useful, but maybe we'll have a bit more luck with the web view. So let's jump into the web view. And then we get this giant graph. And this graph starts off with the top being the entry point and each arrow showing you function calls. So basically, at this point, it's saying that serve spent 7.63 seconds in total, of which 2 seconds were spent by the function read request, 2.5 in finish request, and 3.12 in serve HTTP. Each node has a lot of information about exactly how much time was spent inside of it. So the 0 here represents the time spent inside of finish request. versus the 2.5, which is the total for finish request and any functions it called. We have a lot of data here, and this is still a little bit hard to kind of figure out what exactly is going on. So let's try GoTorch. So GoTorch is, let's have a look at the help. We can do the same thing and specify a URL for GoTorch to hit. So we just have to specify the base URL here, localhost. And then we should tell it time as well. So we want 5 seconds again. So under the hood, it's calling pprof and then generating some raw output, which it uses to convert to the flame graph. So let's open the flame graph. The flame graph is almost the opposite of the graph because it starts at the bottom. The bottom is the entry point to your program, and each level up are the functions being called. Straight away, you can kind of see that the flame graph has made it much easier to see that your program is really divided into 3 main things it's doing. You can see that there's reading on the left side, and you can see like all the functions have read in the name, and then it ends with syscore.read. There's the write, it ends with syscore.write. And then this is where our handler itself is running. And you can tell it's the handler because it uses serve HTTP. We can't really optimize the reading and writing. That's handled by the net packages and the runtime itself. So let's jump into our serve HTTP and see what is slowing it down. And like you might have guessed, it's something to do with our stats. So we can see here that with stats is pretty much using up all of the time. Let's click into with stats to zoom in even further. And with stats is using a lot of time in get stats and then os.hostname. So as you might be able to guess at this point, os.hostname is actually what's causing a lot of our time to be spent. So let's jump back into the code and look at this, look at where it's being called. So just like we saw with stats calling get stats calling os.hostname, you can jump back here. You see that with stats is calling get stats tags and get stats tags is calling os.hostname. Now, turns out os.hostname is pretty slow and we probably don't want to call it every single time. os.hostname is something that doesn't really change very often. So why are we calling it every single time? So what we should be doing here is probably creating a variable and then setting it once and then using that variable in our code. So let's have a get host function, move the logic that we have into that function. So if there's any errors, we don't want to set it. And otherwise, we want to truncate the host name if it ends with, we only care about the first part of the host name. And then we would use that variable here. So if underscore host name is not equal to blank, then set it. That's it, right? So let's have a look at, see how this affects our runtime. So let's go back to our profile that we had running. First, let's profile the old one again, just so we have a number of how long it's taking, just so we don't have to run the previous benchmark. So now it's at about 36,000. Let's restart the server since we've changed the code. And make sure it's running. Run it again. There we go. So just making that one small change got us up from about 35,000 requests, 36,000 requests to 43,000 requests. Still not, it's a lot better, but it's still not great. We can do better than that. So let's have a look and see what else is taking up our time. So let's start the load testing in the background just so we have some traffic to work with. And let's hit pprof again. So we're going to do another 5-second profile. And this time, you see that it's much clearly dominated by the writes. The reads and the writes are a big part of it. Your handler isn't taking anywhere near as much time. And this makes it even harder to normally see what's going on within your handler because it's such a small percentage of your program. But luckily, you can just click in, zoom into just the handler part in the flame graph and figure out what's going on only within your handler. Scope your problem to just this. So here we see that, hey, look, with stats is still taking up all of our time. This time, we have a couple of different things. We have ink counter and record timer, but both of these call the same next function, add tags to name. So that tells us that these two add tags to name are probably making up like 80% of our request handler time right now. So how would we benchmark this? We could keep doing what we did, which is run the GoTorch, but that actually gets a little bit harder as you're dealing with smaller and smaller amounts of the request time. So in this case, what we're going to do is we're going to write a benchmark. Luckily, Go makes it really easy to write benchmarks. So I've already got a test in here. Normally, tests start with a test prefix. The only difference is for a benchmark is that it starts with a benchmark prefix. So let's do that. And instead of a testing.t, you take a testing.b. And the API, the kind of requirement, the contract is that you run whatever code you're trying to benchmark b.n times. So in this case, we want to run this code b.n times. And we need some tags. Let's actually just copy some tags from the test and set a host as well, because there's no host in this. My host. All right, so that's our benchmark. Now we can run this using the go test command. So go test -bench dot. And I also like to add -bench mem, which records the number of allocations in every single iteration. Now, I do this because a lot of the time you'll find that the number of allocations is very closely correlated with the performance of your code. Anything in the hot path, allocations end up costing you time. So let's have a look at how this is doing right now. Okay, so we're seeing about 6,000 nanoseconds per each operation. So for every single call to add tags to name, it's taking about 6 microseconds, and it's doing 16 allocations. So now that we've written a benchmark, the advantage is we can get a profile out of our benchmark very easily by passing the -cpu profile flag. So we can just do prof.cpu. And now when it runs the benchmark, it's also profiling it, and it's generated these two files, prof.cpu, as well as just a binary of your test. The reason it generates the binary is that pprof needs this binary to basically figure out what the symbols are, because the profile itself doesn't include symbols because it has to be as fast as possible. It's basically recording binary, and it's a binary format, and then the stats.test has all the symbols you need. So let's have a look and see what's going on. Let's try the command line first. Okay, so we can kind of see that it's something related to regex. And here we go. We can kind of see again that it looks like it's regexes, but we're not exactly sure how these regexes are being called. So at this point, we can try this list function. What list does is it prints out the function and the code, as well as how much time is spent on each line. So here we can see that a lot of time is being spent in, where is it gone? Here, this clean is using up a lot of time. So the total time used by this function is 990 milliseconds. 830 of that are in this clean function. So that sounds like a lot. What is this clean function doing? Let's list it. It's using regexes to replace a bunch of special characters with dashes. That doesn't seem like something we should be spending that much time on. So let's jump into our code and see what we can do. Okay, so we've got this clean function here. Regexes are pretty general. They're great for a lot of use cases, but in this case, we know exactly what we want, and this is in the hot path. So we should avoid regexes here. Well, first we should profile to see if we can do any better, and then if it's faster, we can replace it instead of the regex. So let's do that. What's a better way of doing what we're trying to do here? Well, all it's doing is replacing special characters with dashes. So we can basically do the same by iterating through the string, checking the character. If it's a special character, append a dash. Otherwise, use the original character. So we can let's do that. Unfortunately, strings are not mutable, so we have to use a byte slice to do this. So let's go iterate through the string. We need to now look at the character to decide what to do. So we go use a switch to look at each character, and we go, if it's a special character, so we've got a list of special characters in our regexes. It's the curly braces, forward slashes, backslashes, and then space and /t and the period. If it's one of those, then we want to replace it with a dash. Otherwise, keep the original character. And then we don't need to use our regex anymore. We just convert the byte slice to a string. So let's see. First of all, let's make sure our test still pass. So go test dot. Yep, that's great. We do have some tests for making sure that the cleaning works. So you can see kind of here that It's testing the cleaning, so we're pretty confident that our code still works. You don't want to be changing your code while benchmarking without having a solid set of tests to make sure that your changes are right. So now let's actually run the benchmarks again. So before, I think we were seeing, was it about, it was above it was around 3,000. So now I think we're at 2,537. Okay, that's a lot better. And we removed an allocation as well. That's great. So that's still a lot longer than I would like to spend on this function though. So let's keep profiling. So let's use goToolPprof. And again, we see this, let's have a look. We see a bunch of things like grow slice, new array. It's kind of hard to figure out exactly what they're doing without source code to match. So let's use list. So the list function now shows that, whoa, is our clean function still taking up that much time? Let's just make sure that we change the clean function correctly. Let's make sure that, let's actually do this again. Okay. Look at the web view. Okay, so now we're seeing that a lot of the time, most of the time in fact, is being used not by clean anymore, but grow slice and strings.join, right? So why are we growing slices? Let's try to look at list add tags again. So we're growing slices. This is kind of hidden here, but basically all these appends here. We're doing appends, and the slice was nil by default, so it had to grow the slice to append any elements to it. If we look at the code, we can kind of see that we know exactly how many elements are going to be in there. It's either going to be 3 or 4 elements, right? So when you know how many elements are going to be in a slice, don't just use var, but make it so that you can specify the capacity. You can say that the capacity is going to be 4. What that means is it's now pre-allocated its space for 4 elements. So when you do 4 appends, no extra space is going to be allocated, no growing of slices, and so on. Same thing for parts. The only difference with parts is that it appends the name by default as well. So let's do that. 1 element and 5 is the capacity, and we're going to set the first element to name. That's it. Let's now see how the benchmarks change. There we go. So we went down from over 2,000 to 549 nanoseconds, and all we did is set an initial capacity for some slices, right? Now, we've gone down to about 10 allocations. That's a lot better than 16 allocations, but I think we can do a little bit better. So let's have a look at our profile again. All right, so it looks like still a lot of time being spent on these appends, and then the strings.join. That's what's really costing us right now. So sometimes you got to kind of look at the overall problem. You can't just optimize single things. In this case, we're using a whole bunch of temporary objects and using strings.join to generate our final string. What if we could avoid all of these temporary objects to begin with? So we look at the whole implementation and go, you know what? I think we can do better if we just write out the string to a bytes.buffer instead of appending it to a slice and then joining them at the end. So let's do that. So that, there we go. So we no longer need this parts thing. Instead, we would write out directly. And every time we get to a new iteration, we need to put a period in between because that's what our join was doing. So we're going to write out strings here. What we don't want to do is do a string append because string appends, again, are going to do yet another allocation. Why do that when we can just break it into 2 separate calls to buff.writeString? So we're going to do that, and then we're going to write one more thing. And now we look at clean. Clean is still doing a couple of allocations here because it's making this slice, and then it has to copy it to a string. Why create a string when we could just pass the buffer directly to the clean function and have it write to that buffer? So let's say write clean, take a bytes.buffer here as well, and instead of creating any array, write directly to the buffer. And then again here. And then we no longer need to write here, we just pass it, so clean value, write clean I think it is, to buff and v, and now we no longer need to do a strings.join. We just convert the buffer that we've created directly into a string. We have, I don't need this anymore. We don't need to return anything from write clean. So we've just rewritten our code to write directly to a buffer instead of using any temporary objects. Let's see how that goes. Well, we need a 75. Oh, I forgot to change the return type. There we go. Let's try that again. There we go. So we've gotten it even lower now. But the more important part is that we reduced the 10 allocations we were doing to 2 allocations. And the performance now is 339 nanoseconds and up. So we've made it pretty damn fast. Now, you might want to go, where are these 2 allocations going from? Let's say you really wanted to get rid of these allocations. This is the point at which, instead of a CPU profile, you would use a mem profile. And it's almost the same. Just replace CPU with mem, run the same commands, and now Go is going to be profiling your memory allocations. So now you look at the output. And, oh, I forgot to pass -alloc_object. So memory profiles by default are trying to look for memory leaks. What memory is still being referenced? In this case, no memory is being referenced because we've finished the program. We just care about what allocations happen. So you pass -alloc_objects. And it shows us there's 2 allocations happening. One when we're creating this original bytes.buffer, and then one at the end when we're writing out the buffer to a string. So the one at the very end, we can't really avoid that. We have to build a string to return the new metric name, and that has to come from somewhere. It doesn't just come out of nowhere. So that's the allocation we're gonna need. But there is actually a way you can avoid the other allocation. The creating the bytes.buffer can be avoided by something called object pooling. So object pooling is basically a way to reduce pressure on the garbage collector. Instead of creating objects and leaving them, you actually put them into some sort of structure, maybe a channel, maybe an array, so that you can the next time you come around, you reuse the buffer that you made earlier, right? So Go has a inbuilt type for this to make it a lot easier called sync.pool. Sync.pool is great for objects that are really cheap to create. For example, there's no pre-computing needed, or there's nothing to warm up like a TCP connection. If it's something really easy to make, for example, like this bytes.buffer, sync.pool is great. If you need something for other stuff like TCP connections, don't use sync.pool. Use something like a channel or create your own object pool. The main reason is that sync.pool gives you no guarantees that it's going to keep the objects in the pool. It can clear them anytime the garbage collector is run. So let me show you how we can use sync.pool. It's actually surprisingly easy. You just need to create a sync.pool and you give it a new function. And because we don't have generics, we return an interface. All right, so this is it. We've basically defined how you create a brand new buffer. And now instead of creating buffers using our bytes.buffer, we're going to use our pool. And we need to cast it because of generics. And when you're done with the buffer, this is the important part when you do object pooling is you need to put it back in the pool. You need to say, I'm done with this object. You can reuse it now, right? So defer is great for doing this. And another important thing is you need to reset your buffers, because if you don't, let's have a look at our tests. Hey, look, the metrics don't match because it just keeps appending to the metric name because we never reset the buffer. So make sure you always reset your buffers. And then let's run it again. Oh. So this time we see that performance actually got a little bit slower, but we did get rid of that allocation. So we only have one allocation. So this is why profiling is important though, because you can't just apply the same set of patterns, like always use a pool. Doesn't work clearly, because in this case it actually got a little bit slower, which is why we probably want to go back to our original implementation of just using a bytes.buffer. And that's because bytes.buffer has been pretty optimized for kind of small use cases like this. So you don't really need to optimize it. You don't really need to pool it unless you're writing a giant amount of data to the buffer. So now we're back at 339 nanoseconds and up. Let's now see how it performs compared to our other handler. So we can do the simple endpoint again. Oh, my server's not running yet. So let's run the simple endpoint and then the hello endpoint. So the simple endpoint is still around 57,000, nothing's changed. So this was kind of varying between, I think, 38,000, 40,000. Now the performance is closer to 50,000. So we really got that performance up because of our profiling. Yeah, I think that's all I had for the benchmarking. Let's get back to the presentation. All right, so this is just a short list of commands that we used in the interactive session. So if you ever want to use this as a reference or figure out what I was doing, I've got them all here. Some lessons. The first one is don't prematurely optimize code, because why would you optimize something that doesn't actually impact your performance? Go makes it so easy to profile your code and find out what is really slowing down your code. So profile first, then optimize your code. Use the tools that are built into Go. The second thing is avoid allocations on the hot path. We just saw that we went from 16 allocations to 2 allocations, and we brought down performance from, I think it was over 3,000 nanoseconds to 300 nanoseconds. So it makes a huge difference when you're allocating in the hot path. You might need to pool. Sometimes pool will help you speed up your code a fair bit. Sometimes they won't. So you should always make sure you have profile benchmarks written so that you can really see whether something's beneficial. And the other thing is, don't be afraid to look at the disassembly. Sometimes you're going to see things like, hey, this function's using up 2 seconds of my time. Why is it using up 2 seconds of my time? And what you'll find is that you can't tell unless you jump into the disassembly. So I'll show you an example of the disassembly. Let's just go this list. So let's say we were looking at list add tags and you said, hey, I don't know what exactly about write clean is using up my time. Well, let's look at the disassembly for write clean. And it shows you, hey, look, it's this exact call to bytes.write bytes. This was easy because this was already in the function. But a lot of the time, you'll see calls to the runtime that you wouldn't otherwise be able to see. The only way to see some of these things is by looking at the disassembly. You don't have to understand all of it. Just get a look at the function names that are being called, and that's usually more than enough to help you figure out what's going on. And that's it. So does anyone have any questions? Yeah?
Yeah, great talk. I hope it's recorded so I can show it to some other people afterwards. I just have one question. If you go back to the pull kill, you use defer, and that can sometimes be somewhat expensive, relatively speaking. What would happen?
Defer?
Yeah,
Yep.
what would happen if you do it with the pull but don't use defer?
Yeah, so defer adds about 50 nanoseconds, so you're right. In this case, defer is probably is the reason that it's slower. But at the same time, you don't really want to avoid, you want to avoid having your code kind of split out over different places. So I tend to avoid defer if it's a very simple case. Like, for example, if I'm doing something like v equals like read s.state, then I can do like m.lock and then m.unlock, and that's not so bad because it's pretty easy. In a case like this, it's a little bit more complicated because imagine that someone changes this continue to a return. Now all of a sudden we're not returning things to the pool again, and it becomes a little bit inconsistent and harder to figure out what's going on. But yeah, I think that's definitely a great point. You should try this code. I'll send it out, and you can try it without the defer to see if it actually gets any faster.
All right, thanks.
Cool. Any other questions?
You mentioned that the kernel patch is required to make a list, and it's not required out of contain actually.
Yep. So yeah. So on one of my slides, I mentioned that this slide here, I think I mentioned that you need a kernel patch to use pprof on OS X. It's only needed if you're not on the latest, which is 10.11. They finally fixed it in 10.11, but if you're not on 10.11, you need to go to this URL. There's a kernel patch that Russ Cox has put together, and hopefully you trust Russ Cox enough to patch your kernel. All right, any other questions? The question was, does Torch work with blocking and memory profiles? There's been some work to get it to work with memory profiles, but to be honest, I haven't even tried it with a blocking profile yet.
Does it work with custom profiles, or do you have a plan to an arbitrary number of custom profiles?
Sorry, can you? I didn't understand the question. Can you repeat that?
Do you have a plan to support custom profiles?
The question was, do you have a plan to support custom profiles? So right now, the plan is just to make it work with pprof profiles, because we're actually depending very heavily on pprof to parse the profiles, and we use pprof's raw output to convert it to a graph. So maybe the other easier way would be if you had your own format you wanted to support, convert that.
Actually, you can use pprof type of output to output your custom profile.
If pprof supports it, it might just work.
Well, we can talk
Yep.
afterwards,
Yep.
yeah.
Sure. All right. Any other questions?
Are the slides online?
I think they are. I think Cassandra should have a link to them. Yep. Cool. All right. Thanks, everyone.